Yeah, sorry for the delay, a little mess up with my laptop battery. But anyways, I will be talking today about the new VFS module we introduced for supporting the rate limiting for the Samba. And yeah, just to get a quick intro for me, I am Avan, working at IBM, some experience with self storage, and currently working at the self-assembly team. So what I will be covering today, so yeah, of course, why we need first the VFS module at the first place, so some requirements and the motivation behind it. Then I will go through the design of it, and how we enforce the limits in the async IO path. And then, yeah, of course, the evolution, basically how we started with the initial implementation till good enough model, burst level plus the cluster wide. So yeah, of course, from boring to the interesting part, we'll see all of it. And yeah, as I mentioned, then some challenges which we faced while implementing the cluster-wide solution, and once we have all that, then how we do this integration into the self-assembly QoS, basically the management part of it, for which I will show the demo recording as well. So let's get started. So yeah, basically the problems as the self-SMB deployments growth. So we do see the multi-tenant environments. We do see the shared resources like different teams hitting the same self-FS backend. Basically meaning they will be underlying using the same self-FS sub-volume, on top of which they create the SMB share, mount it, and so forth. So now given different teams, departments use the same SMB or the underlying backend, there will be, of course, a noisy neighbor problem because we didn't have any control over the IO, or basically at a share level where we could limit the user to a certain limit, like I can have like 100 IOPS per second or things like that. So that was the need, and yeah, the motivation behind it was, so we had to introduce something which fits these requirements, and of course it should be still not affecting performance much, minimal performance overhead. Yeah, and given you once have this limit set, yeah, the user can set this accordingly and have a predictable performance for the same. So for implementing this, what we need, what were the design requirements? So of course, as I mentioned, we should at least have at a shell level granularity. So it should be a per shell model. It should be, given we are introducing this at a async IO path, so it should be compatible with the Samba async IO, the internals, so it should be async IO compatible. Then it should be a stackable VFS module, because given the requirement currently is for the self-FS backend, it can be any other backend, so it should be easily pluggable for any other backend which plans to use this rate limiting module. And yeah, as I mentioned before, yeah, it should have a minimum performance over it. It shouldn't be like you try to limit, but you lose the overall performance. So yeah, it should be quite minimal, and it should have the controls enough. Like for now, we have started with the IOPS and the bandwidth controls. And yeah, it should be, of course, user friendly, so configurable via the SMB configuration. So yeah, with this design requirements, we then move to the architecture, how we design this stackable VFS module. So in order to do that, yeah, we need some hooks for the async read write paths, for example, in the VFS Ceph. So we need to hook into those paths and then apply the limits. So basically, from the SMB configuration part, you can say like VFS objects mention first the rate limit module, then the particular backend. So it will first go through this module, and then it will pass over further to the backend you have used. So yeah, that's how we can hook. And so this module is based on token, the bucket algorithm. So that's why I'm mentioning here. It checks the available token based on some logic we have done internally. And both IOPS and bandwidth have individual tokens defined for it, and also for the read write separately. And yeah, then it somehow does some delay calculation based on the availability of the tokens, and based on that, we don't block. Basically, in case if the limit, whatever the user set is exceeded, we don't basically block the operation, but we delay as per the delay calculation. So we inject that delay using the T1 timer, and then once that's all done, we forward request to the VFS module, or either it gets delayed. And yeah, as I mentioned, this is how the configuration looks like for the VFS object part. So next, diving more into this, the implementation part. Sorry, and how it works, the token bucket algorithm. So basically, the tokens here mean what's the allowed IO capacity the user may configure. So let's say if you choose the 100 IOPS, so we put the same tokens available, so it will be the same, like we do refresh at the same rate, like 100 tokens per second will be available. And bucket is like a maximum capacity, like until what point the user will say, okay, and if this many IOs are coming in, I can handle their workload. So that's the maximum capacity I want to define. Based on this token allowed and whatever available, we do a refill. As I mentioned, we do keep refilling at the configure rate, and this all refilling is done based on the elapsed time. So we do internally store certain things, like tokens is one of them, and also the last time the operation happened. For example, a read or write operation happened, so we do store that time and then calculate the elapsed time based on this current operation, and do the refilling based on this elapsed time passed. So which will give us that what are the number of the tokens available. And in case if the system is idle enough or not doing IO for a while, like for a certain few seconds or so, it all depends on the elapsed time, then it will return to the full capacity, basically meaning the bucket, the maximum capacity. And how it works later is, like, once you have this token available calculated, it will subtract based on it what's like in case of the IOPS case, you only need, like, you're consuming one token. In case of the bandwidth, it will be depending on the number of bytes which it's trying to read or write or whatever, and then it subtracts that, and then it checks what's the balance available. So if it's positive, it will just move on. Okay, you are good to go, you can do the operation. It will forward it to the ZFS further. And if it's not, if there is a deficit of token, so as I mentioned, we'll just calculate the delay, like for how much we do at the microsecond level. So it will calculate the delay and then just inject timer based on T1 timer. So but it will not block or sleep the operation. So yeah, that's a positive thing about this. And yeah, so this is how the basic configuration look like for the initial implementation. As you can see, the ones which I have grinned out in the VFS objects, AIO rate limit module is mentioned, and then for that module you can mention all this certain configuration, like for example the IOPS limit for read, the bandwidth limit. And yeah, for this delay max, so in the initial implementation we started with something called this delay max value. What this means is, like, what is the maximum delay we should afford for this read or write operation. So this could be helpful in case if there is a certain bursty workload, like that you set 100 IOPS limit, but you got a certain 500 or 600 spike then in that case, user can configure this delay values, basically increase it as per their need, and that will help them dealing with this bursty workloads. But yeah, it's, this initial model is still not that user friendly, so that's why you will look now like what worked and what didn't work with this this initial implementation. So what worked well? So we were able to achieve the per share, IOPS and bandwidth control for both read and write. But yeah, this is per process rate limiting. Basically, each the VFS model I talked about. So each SMBD process will have this limits enforced independently in the cluster. So if I configure 100, so each process will be using that limit throughout for each process. And yeah, we have dual control, as I mentioned, for IOPS bandwidth. And yeah, it's a non-blocking operation, given we inject the delay and don't block or do a slip. But yeah, where it fell short, so it's a per process and not cluster-wide. So let's say a user configure this 100, but now there may be like many processes, 10 processes. So it's like in for that 10 process, you in the overall cluster, you get like 110, like this. There is 1,000 IOPS limit overall, right? Like if you allow, because each process is enforcing its own limit. So this is not optimal at a cluster level. So we need something next at a cluster level. Also, the burst handling, as I mentioned, if you get a sudden spike, in that case, it's not dealing it that optimally, because user will have to then, or the admin who configures will have to think and calculate and inject or put the the delay max value accordingly. So there is some calculation involved on their end, so it's not quite user friendly for burst handling. Also, there is no state persistent, meaning in case if VFS reconnect happens, whatever state was before that for the configuration we store, it loses it. So again on the reconnect, they will get the full IOPS. So this may corrupt the other users who may already doing the IO for that share. So if someone who reconnects, that may that will eat up this whole the IOPS which were set. So the state persistence was lacking. And also, if you have seen in this, in the bandwidth limit, I have to specify the number of bytes. So that is not quite user friendly. Like if I have one, like user want to mention 10 gigabytes, okay, then he has to do conversion bytes. So it's a minor thing missing, but yeah, it's still something not so user friendly. So now we have all the limitation defined. We move on to the enhancements one by one. So we first started with the burst challenge. So yeah, as we know that real workloads can be bursty, like some periods it can be idle or low activity, some certain highs you can see. So it's not a constant steady stream. So in that case, in our initial implementation, the bursts get throttled immediately. There is no buffer for the short-term burst, and this may cause some impact to the performance or stutter performance, and also the long-term average which you would have set may not be achieved in this case, because it doesn't deal well with the bursty workloads. So how do we solve this problem and make it easy for user to configure as well? So we introduce something called a burst multiplier. Basically, in case, let's say a user want to mention that for the 100 IOPS limit, a maximum workload burst I could handle is till 200. So they can simply set 2, or basically from the configuration perspective, they need to mention a burst multiplier value of 20. We do a 10 conversion. So basically that means that that's a 2x. So all they have to mention, okay, I want 2x burst workload to be supported, or 3x or whatever. So that's quite easy for them to configure as well. I have presented here the comparison, the traditional and versus the burst multiplier. So as you can see in the traditional, the capacity is the rate. So for the 5000 IOPS limit, I get this much token capacity, but in case of the burst multiplier, now I have a large pool. I mean, it depends on the multiplier defined. We have a 1.5x as the default. So the tokens available now will be based on this multiplier getting run. So in case of now, we will, if we go back to the bursty thing, the bursty workload part, then in case of certain spike happens, it will be able to deal with the scenarios because we will have enough tokens to deal with that, and not many will fall into the delay zone, or not many operations will get that. So we will have something more well defined and configurable as well. So in the SMB configuration, you can mention something like read burst mult and write burst mult. Yeah, you need to multiply 10 and mention as the value. So for 2x, you need to mention value as 20. So yeah, this was for the first enhancement part. Now the next, yeah, it's a minor one for the bandwidth limit, yeah, human readable bandwidth limit. So yeah, we in the previous implementation had to specify the bytes. There was no way we could do, yeah, simply mention a K or KIB or something like that. So now we have a support. Basically, for the 10 gigabytes, user can just say set read bandwidth limit equal to 10G, and that's it. It will convert into bytes, and then the supply limits accordingly. So yeah, it's a minor improvement, but still helpful. Okay, the next is yeah, the state persistent challenge. So the issue, as I mentioned, the token bucket state lives in memory only. So yeah, on the SMB restart or the VFS module reconnect, or even a shared disconnect, reconnect, or any other process termination happens, so we lose the state, it resets to 0, and again we will have a full burst capacity available. So yeah, it will impact at scale. For burn or limits, it will get amplified to at the cluster level, because so far we only had a per process implementation, and as this restart or things grow up, at the cluster level as well, these limits will get multiplied, because depending on the number of process handling this limits. And yeah, the short spikes can overload the backend system, and further it undermines the QoS guarantees which we may give. So the goal is to preserve this token state somehow, and that's why we can use the TDB files. And we just did the same. We just added a specific TDB file for this to store some information, like the tokens is there, timestamp from basically at what time this read operation last happened. So we store as there. So IOPS tokens, bandwidth tokens, and also to just for the sake of any future schema changes, we haven't kept a version as well. It's currently 1. So we do store those. And this is basically a key format. So if you run a TDB dump on that rate limit TDB file, you will see a share slash its name and the read or write operation, as I've given the example. And this state of the token state is stored periodically every 30 seconds. Right now it's not configurable. We have default put it to 30 seconds. So which doesn't happen on every IO, but yeah, we do save it periodically for now. And yeah, so now we do solve this problem. Yeah, as you can see, I want to start, restart, reconnect, whatever happens. So if the process reconnects as well, or your VFS reconnect happens as well, upon the initialization, it will see that if there is any TDB file already on this node, if it's there, some data is there, it will just read through it, use those values, and then apply the limit further. So that's the advantage we got with the the state persistent. Now the last and the most important, the cluster problem. So as you can see in the image, so far we had, so these all nodes are part of a cluster. So if we set 10K IOPS limit, now each will enforce this 10K IOPS limit, and yeah, they further, I mean, the request goes further to the backend. So it was like 30K IOPS. That's what the SFFS backend has to deal with. So, well, of course, that violates the QoS property. So we had to level up and have a solution at the cluster level. So yeah, here I just specify like yeah, with some MIDI nodes, yeah, each mentioned. So yeah, the actual load will get limited into the number of the nodes which are part of the cluster. So how do we solve this? So we go step by step. Like first we need something which coordinates cluster wide to the nodes or to the processes somewhere. So these were the requirements. So we enforce, yeah, that's the very first thing, enforce global limits across the cluster, ensure we have a fair distribution across these processes, because we are anyways dealing with at a shell level. And yeah, it should automatically adapt, like in case if process joins or leaves, or node joins or leaves, so it should recalculate the limits accordingly and then apply it throughout the cluster. And then it should also, yeah, for the coordination purpose, should use some kind of messaging. But also it shouldn't be excessive that it affects the performance or something, or not a panic. So we have to keep that in mind, the minimum performance overhead. And also it should scale to the large cluster. And in case if something goes wrong, it should still at least be able to fall back to the per node limits if in the worst case scenarios. And yeah, it should have a fail-safe behavior. It should not break functionality, as I mentioned. It should still fall back to per node limits. It should have minimal performance overhead, and yeah, it should have a single point of failure. So with all these requirements, we first came up with a naive approach. Basically, what we come up was with like every process broadcast to the every other process. So basically what this means, I'm not sure if this was fully visible. I think somewhat. But if you can see, okay, so this was basically the summary, basically, which each process will broadcast, like the PID, what's the recent number of IOPS, and what's the incoming IOPS, basically the in-flight IOPS, and the operation. And this info, it will broadcast to every other process in the cluster once per second, just to keep things up to date. I mean, so we kept 1 second broadcast for that, and it will also say that okay, I'm active or not, so the other process can calculate based on that. If it's active process, what's the summary I'm getting from it. And so how this works is basically each process will receive messages from all the others. It will count the number of the total active process in the cluster and do the fair the fair share of it. So if let's say 10 processes are there in the cluster, it simply means it will divide by 10 for all the processes. So for 100 IOPS limit for all the processes in the part of cluster, each will get 10 IOPS. And then based on this limit which we get, it will then update its the token bucket state, and then it will keep on repeating this every second. But as you can see now in the figure is attached as well. So this all communication we did with the messaging structure. So it's just we say message send all. So yeah, I mean, seeing that itself is at the scale doesn't look good, because in case if the process grows thousands, then well, the number of messaging flows are like almost 10 million, or okay, 1 million, close to 1 million messages flowing for 10,000 processes in the cluster. So which is not so good at this at the scale level, at this much scale. So we need to bring something and which coordinates at the node level instead of the process level. And yeah, I will thank Ralph and Volker for this, for pointing this out, and also suggesting a kind of solution, we could or take a motivation from the notify the proxy daemon, and that's what we will see, that how changing the hierarchy from process level to node level we can achieve our cluster-wise solution. So in order to do this, how we do the coordination? So there are two things. The key idea here is to first change the hierarchy, of course, from the processes to the node level. We will just do the coordination through the nodes, and we avoid all this process level mess, which we see that process has to coordinate to the other process and all, which is of course not scalable. And so by two level coordination, what I mean is like there should be one local where there should be something the process sends to a common daemon also, and other is the cluster wide, which the daemons on the nodes coordinate with each other. We will see that in the next slide. And yeah, as I mentioned, like by local, that means the SMBD process reports to a local load daemon, and yeah, the daemon section, the load level summaries. We will see all this in detail in the next slide. And yeah, it still use this the messaging infrastructure, but yeah, the different hierarchy level. Now with this model, I think we reduce our complexity from the n square, which is the number of the processes, to the m square, the number of nodes in the cluster, which is why, I mean, yeah, that's, I think it's well scalable at even if you consider like 20 or 100 nodes in case if there is a CTDB cluster. So let me just go through this image now. So for this two-level coordination, so we did introduce something daemon, local daemon, a rate limit D daemon, which will run on each node. And now instead of the processes doing all the coordination, these daemons will take care of doing this node coordination. So basically it will keep track of the certain things like what are the number of processes running on this node, and it will have a node summary which it will then broadcast to all the other nodes in the cluster, and then it will know that what are the number of processes now running on my end and on the other end, and which it can then forward it with the CTDB messaging to the process. So the process then can just directly consume that and do its calculation again, do the fair distribution again, and then apply the limits accordingly. So as you can see in this, yeah, I think this, so this is the rate limit daemon running on each of the nodes. So on the node 0, I have shown like 4 processes running. On node 1 are 2, and this is 3. So what it will do is basically this will broadcast, hey, I have this many processes running. You can update your count accordingly. So the node 1 will receive, so basically the broadcast, what I'm storing is the VNN of the node. So in this case, it will be like the node 1 will be getting VNN 0, and it will get then what number of processes are running on that VNN, and the same goes to all the other nodes in the cluster. So then with this count, they can then update internally, and also then can send further to the process. So for the process part, I have seen, okay, yeah, I think it's kind of visible. So the handle node summary message which you see is the code on the VFS module side. So once it receives this summary message from the this daemon, so basically before this, I need to mention that, okay, it first needs to connect to this rate limit D daemon, and once it's able to connect, it will then receive this summary message from the daemon. It will update its count, and again, yeah, it has to do the same which we saw in the initial model, just do a fair distribution. So now we still have the fair distribution in place. So now with this example which I have seen, which I have shown, it's like I think 9 processes. So overall it will be still divided by 9 throughout the cluster, but we have controlled the messaging. So it's changed the hierarchy, and it is more performant based on the previous model, and we can still achieve the cluster wide with it. And yes, to enable this, yeah, so we have also added the, because we have kept this optional for now, so they can, if you need to have this rate limiting support with this rate limit D implementation, you need to mention this flag while building it with the configure. And once it does, the SMBD is internally starting this daemon, just like it does a cleanup D, I guess. So it will start automatically once it detects this flag. And given if you have clustering enabled, by default we go with this solution, the rate limit D solution. The VFS model will try to connect, then here receive summary and do all the calculation. And now in case it fails, let's say if the VFS model wasn't able to connect to this rate limit D daemon, then in that case it will just it has the logic to fall back to the per node, the initial implementation, which is useful. At least the users will have something in case of the failures until they report it. So, and this is how the configuration looks like. And the final configuration, we just specify the limits, the burst mult, and we also have something called cluster mode configuration. Now this is optional because by default anyways we will put it at yes, given if you have clustering enabled, but you can always set to no if you see any failure, not on the daemon side but something internally on the module or some other failures, you can always disable it and still have the per node limits in the worst case. And now to the integration part, how we integrate this in the, we already do have a Ceph manager module for the SME management. So we just extend this and have some CLI commands, and these are all part of anyways except for container images. And I think I will be showing all those commands in my demo next. Oh, why is this? I need to definitely change this because this should not be the case. Okay, just a minute. Till then I deal with that. I will just go over what's next for this. Now, given we do have this module setup and we are able to set the cluster wide limit, we were thinking maybe put in some more troubleshoot or some diagnostic tool, maybe something like Samba to rate limit, which will give us all the information or the token state, what's the cluster state status for it, and what are the limits set for it, and etc. And also we can detect issues in case of the restart or some troubleshooting. We can even the with the TDB files we can check in if something has gone wrong there. So a broader level tool to diagnose more into this the rate limit module. And so far we only have a per share limit, but we don't have the requirement yet coming for the per client or per user level control. But in case if that is required, then we can extend next to client level, because right now you do see I'm just doing a fair distribution throughout all the processes all the processes in the cluster. But that is still maybe not fair if you look at the per user at client level, because in case if some client is not doing so small workload, but someone may doing a heavy or having a lot of IOs going on, it will still get only that fair distributed IOs, which is not fair at the client level. So we should have something once the requirements comes in. And as I mentioned, the fair usage is there currently, but we will act based on the requirement comes in. I will put all the references. Before going to questions, I will have to please.
Do you want to take a demo maybe?
You have the access? Okay, then sure. Thank you.
the one which was embedded in the file, right? So
Yes,
demo 4, let me
correct.
say. The resolution gets better over time, so
Okay, I see. I
you can only use the trackball.
see.
Yeah, so it looks blurred, but it gets better. What are you going to do?
I'm just
Ah,
setting
okay,
it
the
again.
bursty. Okay.
Maybe. Yeah,
Ah,
it's better.
okay.
Yeah,
Then
thanks.
just play.
Yeah, I'll just do it. Okay. And yeah, finally we are able to display the demo now. So here I am showing first the 3 nodes F cluster I have, just the status, health is okay. 3 OSDs up, I have volume already created. I also have the SFFS volumes created, even the shares created. But yeah, I will list them all one by one. So I will first check the sub status. It's all healthy. And yeah, and the next I will show that I already have a sub-volume, ZFFS sub-volume created, yeah, named ZFFS, and I have 2 sub-volume created for this ZFFS volume. And yeah, in order to plug in or use the SMB management commands, you need to enable the manager module, so I have already have it on, as you can see. And yeah, the next I will show the SMB cluster which we cleared. So it's a Ceph SMB cluster ls, I have that created as well, so it should listed. Yeah, test cluster, and there will be some shares next under that cluster. Okay, let me just, yeah. So test cluster has 2 shares. Yeah. And yeah, the next I think will be most probably the show command. Now this show command is like what are the all commands you have set based on it, what's the resource now, which looks like, so resources like different types as a cluster for the share, for the user groups, all the stuff, what are the things we have configured. So we just look into that. So for the, as you can see, for this share resource, I already set the QoS, the limits already. And yeah, we can also see what sub volume it's trying to, is linked to, and what it will mount. So those are all the details we can see in the show command. And next, yeah, I think of course it will be the QoS limits, which commands. Yeah, I have created a share with the user mode, so you will see our user groups. There is another option more, is the ADDC mode, but yeah, I'm just going with the user mode for now. And the next, yeah, will be, yeah, so once you create the share, the logic is like it will start running the service or bring up all the daemons like the SMB, CDDB, or even the matrix exporter, things like that. So we can now see the SMB test cluster service running. Under that, the 3 daemons are running, so 3 SMBD we have on each node. And yeah, the Ceph SMB share, I think now I will be listing the QoS command. So this is basically how it looks like: SMB share update Cephfs QoS, the cluster name, the share name, and then all the limits you want to set. And I have the cluster mode as well, just in case if user wants to set it no or false in case of any failure. So with this limits applied, I think now I will show you how it gets reflected on the container side and the SMB running on the nodes which we see. So I just did a Boardman PS. Now you can see here that this is one of the SMBD running on that node. So I will just execute into that and just show you the SMB configuration which get set from this F side. So now we can see it has got perfectly reflected. We can see rate limit VFS objects. We can see all the limits we set reflected there. And yeah, with this now we can, I think, do the actual IO and move on to the SMB client node. So that's what I think I will do next. with all this done, I think it should already, yeah. So now I have this well, basically 4 client nodes. As you can see, the first one, the VM0, it is connected to the node 0 of the SEF node where the SMBD is running, and the rest 1 and 2 goes the same individual to 1 and 2, but I have kept the 4th one to the same instance, so I have connected again to the 0th instance. Yeah, okay, I'll speed up a bit. And once we have all this set up, and now I have the limits defined, I will just run a FIO run on these nodes, and yeah, that should be yeah, I just kept, I will run as a size of a workload of 50 megabytes, and I will also be changing a share name. So this is where I want to run the FIO run, and I will just move to that. So okay, at this point I'm so the thing is, and right now I'm doing the IOPS parallelly on all the nodes. So that means I have set 100 IOPS limit, the read IOPS limit as 100. So in that case, what we should ideally see, in case if all these 4 clients are trying to, or all these 4 connections are trying to do the read from the same share with the 100 IOPS slip, it should do a fair distribution. So it should be around 24, 25 IOPS per process, or basically per connection in this case. And yeah, that's what it achieves. It will fairly distribute each on all the things. I've shown the 4th node on that because it is also, so it doesn't matter which instance you get connected to. At the end, it all matters on the number of connections open, the active connections, which does the IO, and it will just fairly distribute among all of them. And next I'm quickly also showing how to debug this and what are the things you should look are working well or not. So the very first thing is, yeah, for your cluster-wide rate limiting is if you have to see if your rate limit D daemon is running fine or not. So that's the very first thing. So yeah, it will show something like started rate limit D. The next, I think it will say, okay, rate limit D is initialized, so it's all working up and running. And at a moment, if the processes have not been activated, have not started their IOs yet, you will see something like, okay, there are no active processes. So the thing is, the daemon doesn't broadcast in case if there is no process running. It will just keep on adding the timer which every second and just skip the broadcast. And once it has the active processes running, it will then start broadcasting or collecting the number of active processes for a particular operation, then broadcast it to the nodes in the cluster, and then further it will give the information to the VFS one. Now on the VFS side, what we should look for is, yeah, if it is able to first connect to the rate limit daemon or not. In case if it's not, then it will show, instead of connect, it will show a failure, and it will automatically fall back to the per node rate limit. You will see in this case, as you can see in this, okay, I will be showing this very quickly next. Like you can see a cluster mode enabled via daemon. In that case, if in case of failure, it will show it was failed to apply the cluster mode, and it will just show the per node is started. And next, yeah, you can see some TDB logs are there as well. So in case if the file already exists, it will just load it and try to extract the information which was already stored in it. And yeah, the next for the rate limit module, the logs which you will look for is like what it's reporting to the daemon. So basically it will register itself. It said like these are the number of IOPS I am getting, these are the number of IOs I am getting, and these are the IOPS, and this is the fair distribution I have currently. So those information it will share with the daemon running on its node. And it on the pre-IO, which you can see next, it will, that's where the actual the read and the write all gets dealt with, and in case and it gets calculated, and even the tokens can refill at that stage, and it will give us the final calculation that, okay, for this operation what's the delay it will get, and why it will get, because we have the IOPS token deficit, as you can say, the minus values for it. So it will list out those logs on that. In case if you see anything, any IOPS not working, you should definitely first check why this limit wasn't enforced. You should go and check the pre-IO logs. And then the next ones is it will handle this summary message which comes from the daemon, and again reapply the limits based on it. And I think that's all for me. I think the demo is done. So thank you, and if any questions, I am ready to take. Yes.
How do you transition into the burst rate limit and out? I didn't quite get that.
Sorry?
For how long is the burst limit applicable, and when do you transition to the normal?
So the burst multiplier which you are setting, it's for the short-term thing. So like it. So let's say you want to configure like 100 IOPS limit. Now you say, if in case if a sudden burst comes in, if let's say a 200 or maybe 500 is coming in, but I only want to allow a 2x. Or 2x means basically up till 200 I will handle, so that many tokens will be available. So the 200 IOPS will get fair, they won't get delayed. Till that point you will have a well balanced without delay operations. But in case if it exceeds 200, those operations later than 200 will start getting the delays, and they will finish accordingly. So the burst is like in case of the short-term burst, like a certain burst, if you see in those scenarios, you can mention this multiplier that okay, at this if the burst is until this point, I am fine. But if it's anyways, if it's more, then it will work as it is. It will start applying delays.
Yeah. So when do you decide that burst is over and the standard limit applies?
Yes.
When? How do you decide?
No, the limit is still it all on the tokens available. So it all goes based on the tokens availability. It will recalculate because it works on the elapsed time. So the elapsed time, if it's over, if it's past the burst workload, at a certain point it will have enough refill to serve the operation later. I'm not sure if I'm answering that clearly, but.
So the burst applies automatically?
No, the user can configure. Based on that, we do the calculation.
Yeah, but if you have the burst configured,
yes.
and then there's a spike, then it applies automatically.
Then it will deal with that, as I
Okay.
mentioned, based on the multiplier,
Okay, two small things. First of all, before you started the presentation, I was still a little bit unclear as to what's the motivation, because saying taming Samba Async I seems to say Samba is just too fast, and I've never heard anybody say that. But I think the main point, if I got it right, is contention if multiple clients are accessing the same data at high speed.
Yes.
So that's the point. Okay.
Yes.
Thanks
Yeah,
for
that's-
confirming.
Yeah.
Second thing is, I was a little bit surprised to see Samba tool mentioned, because my understanding is it's mainly for Active Directory configuration in the server.
Yeah, this is something we still have not designed on it, but some diagnostic tool. So I just mentioned because I was thinking of taking some motivation from similar to the Samba tool part, but
Was
still not.
expecting something like the net tool or SAB control or something?
Yeah, something from that I was thinking, but it's still not designed yet, but that's the next plan.
Thanks.
Thank you.